Okay, the video is running again. And I'm going that way.
Hi, Sam. I love you.
Hey,
Don't
no,
fall.
go in the corner. That's how you
Okay.
win. You have to go.
So, hi Sam.
In the corner.
Hi guys.
Go, Christina.
Merry Christmas.
Anybody want an M&M?
Right through your little
No,
channel.
thank you.
Hey, hey.
So, today we have interesting
No.
stuff to
I
talk
got
about.
right there.
Pendulum.
Now it's my turn again.
Thank you. Oh yeah, I have to look at your homework. I shouldn't have started with you.
This is it. But I already won.
And like actual math.
Sorry. Seriously though, where's your other piece?
You broke it.
No, it came broken and
There it
there's
is. I
one
didn't-
pink bush missing.
How many do we have to go to? Because I had trouble with
Yeah, that's okay. As long as you
I did all the written questions. How many do we have to do?
four
4?
or five, I don't know.
Okay, because I did
Problem.
4
Anybody
written
want
questions.
a chemistry quiz? Anyone?
I can probably switch.
Chemistry
Yeah, I bet
quiz?
you could.
I could.
I
I
missed
know.
5. I wanted to die.
3 questions.
Oh,
and
hey,
practice
remember
problems.
that.
And I think I left one. No, 2 left.
You don't really
Oh, I left. I think I left a few, like 1 or 2.
Once you guys
On the
see like the
practice
theory,
problems,
it'll be easy.
they were
Can
hard.
you look at mine? Okay, it's mine.
Dude,
Yeah, on your
I kind of like.
We don't look in the book like you do.
And then before, but I got lost on the last one before.
He does
like,
work
I
this
got
week.
Oh, okay.
Oh, you
Like,
did?
when is it total energy kinetic?
No, I was just like, where do I go from here? I don't know what I'm supposed to do.
Wait, did
Oh,
you?
You probably have to.
Did you do a lot of work? Or are you being
What
sarcastic?
No.
score.
Kind of both. Like,
Yeah,
it's
it's-
a lot more
Is this a
work
lot of
than-
work?
Yeah.
Just write both equations.
I got
crammed
potential
together.
and kinetic, and then I got the total energy.
I did worse for
First
one
part,
problem.
and
Number
then feel like-
1
You
for
don't
the
need
practice
total
problems was
energy.
easy.
You just need potential and kinetic on one side equation for the first
Number
part.
2 has
Then for the
hard.
second
You're
one,
dumb.
potential and
You're
kinetic.
12th
Oh, so I needed to get potential and
Yeah.
kinetic again.
Yes. Just
For
so
the,
they'll.
for the other, for the
Yeah.
other hill.
Have
part
the
of,
light.
like,
I have
Josh,
those.
should I
So
get
you
your
have
test?
those on each
Oh, me?
side.
Yes, I did, right?
Okay.
Both Josh's.
Oh, wait,
Okay.
I have my test for you and my corrections.
Oh,
Forgot
I
my-
forgot my.
Yeah, I
Dad.
forgot mine. I have
For
to wait
the
till
master.
after
Or
Christmas.
to church.
Look, 2
Well, actually, I can do it after.
Dude, I need to come over to your house when we work on labs.
I just didn't do that one.
I gotta do this.
I
I gotta
did
do
You
all the
guys can come over to
corrections.
my house.
Really? Okay.
Listen,
Yeah, because we are behind
I
on
was just
labs.
wondering, for some
So
problems,
glad
can you have different answers than they have? Like,
For any of the problems, did I get different answers?
no, just for some of them. Because, like, if you keep significant figures, or,
Yes, if you just keep going through and you're
or
calculating
like,
with
if you
your
just
own
keep
step
going
by
and you
step.
don't
I keep going.
reduce.
Sometimes I just do it and I don't go.
Yeah, so can you have
significant
different
figures and I just shoot my
answers
calculator.
I do.
sometimes?
If you have a good method, yes. If you have a random method where you abuse significant figures in the middle and like round wrong, then no.
Okay.
But it's possible that you might be a little different in the book and still looking good. Josh had one that was way different significant figure wise on the test because he used a different equation, so the significant figures were different.
Oh, wow.
Doesn't he
And
usually
it
use
was
different
totally right. It was like
equations?
it was like almost a whole number off of the other way, and
Oh,
it
she was
still was
like,
right
one.
significant
How did
figure
you
wise
break
with
it
that
all the way
equation,
Which
which took me like forever to figure out. By the way,
There's 5 yellow bushes and 3 pink bushes.
so
Right here. Now you
module
got
8.
one. Use a broken yellow bush. That's pink bush. You got 4 and 4. It's even now.
All right,
Oh, I used one. 2 8.
so can somebody define energy?
No.
Yeah,
It's in the book.
Josh.
Energy
The ability to
is...
work.
Matt, stealing the fun. You stole the fun.
You sucker!
It's the easiest one.
Well, okay, well, there's one that energy and then there's another one.
There's work.
Work
Work.
is, work has to apply some kind of action towards it or something like that.
Keep trying. You're getting there.
Displacement? Wait, what?
Yes.
Oh,
Work is
the
moving
ability,
a
object,
with all objects have
energy. Mass.
moving a mass.
Force
What did he just tell you to say?
and
Displacement.
placement.
Okay, so moving a mass through a displacement. That's work.
Was that the
I don't
definition
know
of the
if it
book?
is. That's my definition.
Hold on, because mine...
Let's read the book definition of work.
Okay, can I read
Andy
it?
Griffith show?
Alright, my turn. Everybody be quiet, I'm gonna read. Which hopefully I can remember how to read.
Now think, next question is gonna be, what's the difference between distance and displacement? So go ahead and think about that.
Distance and displacement.
Sam is enjoying the back of Christina's.
Oh, I'm sorry. Sorry. Doing a chemical quiz test.
251.
I can email you that quiz.
Oh, energy work. Oh, the product of the displacement of an object and the component of the implied force that is parallel to the displacement.
Okay,
Energy, the ability to do work.
energy is the ability to do work. Work is moving a mass through displacement. And yes, the component, so what that actually means when it says the component of the force parallel to the motion of the mass. Okay, so like if I'm moving this object through a displacement and I pull parallel to the direction it's moving, then all the force that I'm using to pull it is directed in moving it, right? If I pull like this, then what component of the force is actually causing motion? Not the upward component, right?
The horizontal force.
Right, so I have to
Component.
do the whole cosine sine thing to find just the component that's parallel to the direction it's moving. I wouldn't consider the component that's on the y-axis there. Probably Sam couldn't see that at all. I have to demonstrate up higher, apparently. Okay, so, what task? Oh, what's the difference between distance and displacement, Stephanie?
I know it. Displacement is when you move something distance. And distance is just a distance, right?
Yes, so if I move, I'm trying to think of how to do this up higher
Sorry, Sam.
in an obvious way. If I move this eraser from here to here, then it went over a distance, right? If I move it from here and I go like this, did it go a different distance? If it takes a windy path,
Yeah.
it goes a different distance if it takes a winding path, but not a different displacement. The displacement is a straight line from start to finish. The distance is like the actual length of the path it travels. The displacement is just a straight line from beginning to end. So, that is very important when you're talking about work and power and the things that we talked about in this module. Because the equation for work is the force parallel to motion times the displacement. And so if you wander all over the place, you need to measure the displacement of the object, not the distance through which it went. So what are the units for work?
Is it Joule or? Is that how you pronounce it?
Joule?
Joule.
Just
Wait, no.
Isn't it just like any
Oh, yeah.
force times any mass?
Any force times any distance.
So
So a
It
Newton
says it
meter,
on the page.
a Newton
Oh,
meter
work
is our
equals
standard
F times
displacement.
Sub-parallel.
Right.
Or whatever, how you say it. It's
Yeah,
sub-parallel.
sub-parallel, that
Don't
works.
make me.
So it can be any force times any distance. So you can have wacky ones like dime centimeters or pound inches or pound foot. But the Newton meters are gold standard of metric usage, so mostly Newton meters. Yes,
can it be like a Newton foot? You can't do that, right?
it could, but
Well,
It'd
That
just be
would
really
be-
weird because you'd have to do like conversions and
Okay,
work.
so that's
Just
actually-
because
a ton
the
of
Newton-
conversions.
Yeah.
Cause like the Newton has a meter in its definition, so you have like a meter and a foot in the
Right.
same.
but
So
sure.
meter.
Okay, so it
3
actually
and
could be that.
Four
Sure.
and
Okay.
something meter.
It could be that, but you'd obviously want to convert before you went on to use the
Yeah.
work in
Yeah.
another equation, like in power.
So it doesn't have to be like the same type of. Okay.
It could be, you know, any mile. So, when do you do work? Am I doing work on this wall no matter how much effort I
No.
exert?
I had a question about that.
Unless-
Like, I know that you're not like the answer's no, but
Well,
like,
then move.
what if you're like moving the molecules in the
Yeah.
wall? and
Like you can
how-
dent the
Or
wall.
what if
Like,
I
how
take
much-
a base? What if I take a baseball bat?
But
and
like, you're always affecting the wall, like with
You're
always
pushing
on the
the-
wall.
The
and-
grease on your
so, like,
hands.
how
Yes,
technical
probably
is
the
that?
wall is bowing a little bit, but I
But if
mean, if
you're-
we're
like,
basically
if you're
going
pushing
for
on, like, a
this,
mountain
I'm
or-
pushing on the table and the table is not moving through displacement, then no.
Like if I'm going like this with a pencil and the eraser is going down like that, then I'm
Yeah,
doing
then
work
you're
on
doing
the
work.
eraser, but not on the table.
Well, the table might be bowing
It
slightly.
is a little bit.
Um,
Like if you're trying to like push a
Oh my-
train from the side, you're not doing anything.
Very cheap pencil.
probably, yes. If we're, we should
Cheap
definitely be
pencil.
pushing on something that we can't dent or move at all.
You
But-
won't break it.
We're gonna go with the wall does not bend
Oh,
even under my pushing on it. So, no work is done because I did not move the wall through a displacement. How about now? Am I doing work on this folder?
No.
No,
Why?
because it's not
It's
moving.
not going
What
anywhere.
is?
Well, your
Right,
arm's
yeah,
shaking.
you're-
Well,
But
your
I'm not
arm-
moving it through displacement because it's
Oh.
staying in one
But
place.
it's
Even if it's like this, it's still like not displacing.
It's going
It's
back to
coming
the
back.
same spot.
Right, so like if you walk a mile and you go from here in a big loop around the track and you come back to here, what's your displacement?
Oh, 1 mile.
0.
Oh, 0, you're
Your
right.
distance is a mile, and if you land where you took off, you have no displacement.
So that
I
means,
read
does that
zero
mean even if you walk a
displacement
mile, you
units.
get back to the same
Where did I
spot?
get a mile from? I was like, a mile?
By this definition, kind of ridiculous, right? But I'm just saying this because you get things wrong on the test if you ignore displacement and use distance. So if I hold that book up, it's not moving through displacement. So even though my arm muscle will get really, really tired eventually, I'm not doing any work. Although it's much better than last year because I've been holding that baby. Last year I was like, I'm already tired. Okay, so drop 2 pieces of chalk. I don't have any chalk.
Good job, markers. Oh,
Josh.
oh do you know?
She
hey,
just dropped markers on the ground.
yeah.
Okay,
so
It was
so
very.
if 2 people pick up these
Cool.
2 pieces of chalk, right? Alright, so here I go. I'm picking up one and I put it on the table, right? And then I pick up this one and I write on board.
But what
and
if
I
you
move
drop 2
all
pieces of chalk and it
around.
broke?
That actually happens.
Yeah,
that.
why did he ask you to drop 2 pieces
No,
of chalk?
I just.
Oh, you
my
asked
paper
yourself.
now says drop 2 pieces of chalk.
Oh.
So I'm just reading my direction. So the purple marker went straight from the ground to the table. The
Oh.
orange marker did a whole bunch of stuff. What is the difference in displacement that these 2 markers experienced?
Like an inch from where they're separated on the.
Right. So if they were laying that and they both landed like that, pretty much they went through the same displacement. But how about distance? Which one went through greater distance?
the orange one.
Notice I said this like about 50 times.
On the test, guys.
Guessing on the test.
Right. So, which marker did I do the most work to move?
The orange one. You
Neither.
do the most work because you were drawing all over the place with it.
No,
Right?
because it's the displacement
Oh.
not the distance.
Make sure it's the farthest away from the starting point.
Well, we're assuming that
You
it
did
was
more work
are
on the-
equal.
Feel like a little-
Same work was applied.
Yes, even though I went and I picked up the orange marker, wrote on the board and put it there.
That makes no sense.
I know it doesn't, but that's why I'm going through all these examples, so you let go of work is like I'm going all around doing work. Work is force parallel to the movement times the displacement.
Oh, so work is just measured by displacement, not distance.
Yes.
I'm sorry.
I
That's
even
why
knew that.
my
too.
paper has 3 examples
Okay,
here.
okay, so
Yes.
like if I went like
What are you
this
saying
and then I
there,
went
Josh?
like this, I would have done
You
no
said
work.
even I know that.
Yeah.
Yes, if you move it and then move it back, the
Sorry.
displacement is 0, so no work. By our
That's
definition.
Sorry.
dumb.
It does, it seems
with the
wrong,
straw.
it
Now you
seems
did
not
work.
okay.
Just moved
Yes,
it.
it moved again, now it has a
I'm
displacement,
sorry.
but not nearly as much as you think, cause you don't get to count all that.
The stuff that you think is work but actually isn't is called the exhaustive component.
Exhaust?
It's not actually,
Exhaust pipe?
but-
Work was done.
Alright, so, make sure that when you're calculating force, that you only calculate the component of force parallel to movement. Okay, so if I'm dragging this table, right, is all of my force going parallel to the movement of the table?
Wait, are we
No.
always doing work though? like in our bodies,
Well,
our-
yes, because your body is like,
is always like
That's sort of a different
you're
definition of
digesting
work.
and combusting and,
a heart beating.
yeah, I mean, there's all kinds of work going on.
It's
Moving
going
blood
through
through
the
the
it's
body.
like your
Right,
blood's going
so-
through, so your heart's not really doing any work.
I'm like
weird.
Superman.
There's no net
Oh,
displacement. Right, our definition might have to change for things like doctors and stuff, not just,
Yeah.
well, this is really
Heart's not
funny,
doing
but
any
anyhow.
work.
No, it's
Okay,
just
so-
exhausting.
My heart is not doing any work. Oh.
It's doing it. It's
So-
got an exhaustive component.
So is all the force I'm applying to the table going toward doing work to move the table? No, why?
Because it's going like up this way, so some of it's pulling the table up,
Alright, so when I'm doing this, what do I have to do?
and the
Make
table
it
that you spend.
parallel. Make it parallel.
Okay, so I have to split my force into two components. And I'm only going to look at the x component of this force, so the angle, the cosine. Look at the x component. I'm not going to look at the y component of that force at all. So if I could, if I had like a little suitcase measuring weight and I pulled on the table, I could measure how many newtons or pounds or whatever I'm pulling with. And then I would just have to use the angle to calculate what the parallel force is. That would be the force. I could measure the displacement of the table and I could calculate how much work I did.
So if like instead of going, if you wanted to measure, if you wanted it to just pull this way, instead of pulling like that, and like instead of going down like this, so you pull it straight. What if you went like this? Would that still be?
You're just like,
Would that still have like a angle?
I'd have to look at my
this is where it's
anatomy
pulling.
notes to that, because the force, I guess you are
'Cause
really
it's- your arm
redirecting
is
the
pulling
force
it
in that
parallel, but
direction.
it's being your shoulder is pulling.
I think you're
the whole
redirecting
thing.
the force so that it's really, really parallel if you
Okay.
do that instead of this. Somebody take anatomy so I don't have to think real hard about that.
Oh, I'm taking anatomy next year.
Good, then you answer that one.
Okay. I'll come back just for this class. So I can.
Guys, stop bringing your pencils.
I wasn't breaking. I was trying to
You
write,
really
and
broke
my
it.
super strength is just like.
Shenanigans.
So, now that I've lost my train of thought. Potential energy and kinetic energy. So what is potential energy, Christina? Are you stealing the
like the
fun?
possibility to work.
Okay, so the potential to do work. It's what?
Energy stored up to do work.
Stored energy. Both good definitions.
Yes.
And how about kinetic energy, Matt?
energy and motion.
Energy in motion. Okay. So what is our equation, Josh, for potential energy?
Josh Haynes.
Yes, you.
PE equals mgh.
And what does MGH mean?
Mass gravitational.
No.
You just told me gravitational.
That is
Gravity.
not a word.
Gravitational.
Mass times
Gravity. Height.
good. Okay.
Technically,
Oh my
acceleration
gosh.
due to gravity.
We've
Yeah.
been doing that same equation all week long.
So kinetic energy.
Here,
I did this morning.
Yeah.
Nice.
Yeah, so did I.
In study hall.
1/2 mg squared.
Okay. So those are two big equations here for potential and kinetic
I read
energy.
it. I just did.
So obviously you have more potential energy because height is counted. This eraser has potential energy, right? If it tipped over the edge, started to fall, it would have the ability to do work. If I raise it up, did I increase or decrease its potential energy?
Increase.
Increase its potential energy, obviously.
Would it be like, would potential energy be like a slingshot?
Yes, why?
Stored up energy because it's.
Or like a crossbow.
Yes, just like a crossbow.
Okay, so a cross.
Show Sam your thumb.
Hi, Sam.
Oh, you can't see you.
Wait,
We
here.
said the word
I'll
crossbow
move it slightly.
and
That's
now
my
we see
face.
the thumb, so.
His hand.
Don't put your finger up where a crossbow string is going, just so you know.
It's not good.
They can do a lot of work.
Hopefully you're having fun in Canada.
He's not in Canada.
Oh, yeah.
For 2 weeks.
I thought you told in Canada.
Yes.
I'm just.
I know that.
Yes. Okay, so potential energy is relative. All right. So relative to the floor, this eraser has a large amount of potential energy compared to relative to the table. But what is the reality of how much potential energy this eraser has?
The distance from the top, from your hand to the floor.
Well, it's if
That's
it,
relative to the floor.
It's gonna hit
Right.
the table.
Oh, it's the
right,
distance.
it's
Oh.
gonna fall to the table. So really, the potential energy it has is relative to where it's gonna stop. But it's relative. I mean, it could fall all the way to the
The
floor.
table could-
Wait, what's other stuff that has potential energy?
Like if
What?
you're sitting in a
What's
chair
other
and you're
stuff that
rocking
has
back and forth.
Potential.
And then you fall
Like
backwards.
everything. That wipes
Like a
container.
Bungee
For
cord, like
You
a
got, well,
Yes.
like
A
Don't let it
stretched
snap.
out bunch
oh,
of
or a parachute, like a backpack parachute, because it's stored up, and then when you pull that thing, in, right?
I suppose that is true.
Or like
well,
a
like,
spring,
doesn't
or
everything have or potential energy? Because anything can fall.
Anything
and
with
be
mass.
actually
Anything can be
high
moved.
gravity.
Yes,
Except
but
for
when
the
you're
earth.
answering
I'm just
questions on a
Like
test,
that little pink flower pot that's about to fall off the edge, that is potential energy.
Yeah.
In a minute, it's gonna have kinetic energy when it falls on the floor and shatters.
because
Wait,
it's in
like
my
that.
class, so it's very likely to
So is
happen.
it anything with mass can have
Potential energy. Now, fire does not have, that's kinetic
gasoline
energy.
has potential
Burning,
energy.
combustion, kinetic energy. Now, the wood that's burning has potential energy. But the
That's
fire
easy.
itself, lightning, those two things.
You-
If they ask you about lightning, that's kinetic energy.
So like fire and lightning are never potential.
No, but the thing that's burning has
Okay.
potential energy.
Wait, so
like
fire
the-
isn't potential?
No, it's kinetic energy.
Oh, because you have to
Energy,
light it.
motion.
where would you say the energy
Lightning,
came from for lightning? Like just
lightning's
Clouds.
potential though.
Static-
Lightning
static
is,
electricity.
yeah, it's electrons. It's just
Oh.
like,
So
It's
everything
electricity.
has potential energy. That's crazy.
yes,
everything.
everything has potential
So those
energy.
keys.
Lightning is
the
kinetic
wall.
energy, so when they ask you about lightning, that's kinetic energy. If they say, give an example of something with only kinetic energy, you can make a good case for practically anything having some potential energy as well, so go with lightning. Let's see here. Stephanie, do you know what the first law of thermodynamics is? I know.
I know.
I know without looking,
National.
energy cannot be created or destroyed.
But we've
or
heard that.
change forms.
It can change.
We've heard that.
forms,
But
that's
doesn't-
right.
Wasn't it for
Chemistry.
matter too? Matter?
Yes, but that's the,
I thought the
The
first
law
law.
Wait,
of
isn't that what-
conservation.
Okay.
Isn't that what
Wait,
Stephen Hawking thinks it's not right?
No, he thinks that that's probably right.
Wait, I
Because
thought
it-
that there was somebody that thought that like like
What?
things
Energy
can't
cannot be
be.
created or destroyed, it can change forms, and the it can change forms thing allows for the reason that, like, if we split an atom, a huge amount of energy is liberated. It's because that amount of energy was stored in the nucleus of the atom, holding all those positively charged protons together.
Well, then that means energy cannot be created or destroyed. That means that proves
Big
evolution
Bang?
wrong, right? The Big Bang wrong, right?
Not necessarily. Nothing
Oh,
in
because
science
they
can
say
be
that-
proven.
Because they say that.
All that energy or matter is still present. Like, current thinking on if the Big Bang is true is that all matter that was in the universe was compacted into an immensely dense,
Oh, like a
I can't have
black
it.
dark black hole. A dark.
like a
hole.
like a very, very dense singularity is what they call it, of matter, and everything that was there, and then
So like a black hole influence.
Well, where'd that come from?
exactly.
You guys
What
are
caused it
dumb.
to, and we don't know the answer to that, or even if that is remotely true.
Wait, the answer to what?
But is it sort of like like the inside of a black hole just like blown up?
The inside of a black hole is just mass compacted.
Yeah, but
But it's
isn't that
bringing
sort of the
everything.
same thing, like a bunch of mass and then it just exploded?
Has anybody ever found a black hole?
Yeah, there are lots of black
The
holes.
center of that
That's
one thing we
weird.
looked at, that picture we
Well,
looked
they
at.
say they see it.
But
Because you
it's
can't
just-
see it, right?
No, because it even is so, the mass has so much gravity that it pulls light
How
in.
do you even know what it looks like?
Like, well, yeah.
It doesn't
you
look
can't,
like anything.
You can't really
It's
see
black.
it, can you?
No, because light is absorbed into
can't
it,
see
and you
black
can't
stuff.
see
Isn't
when
that
light is
weird?
absorbed.
And
Well,
Wouldn't
you know
it
it's
absorb
there.
all the light?
That's
So
great.
black
the
holes
only
are
thing
pretty
you find by not
scary
seeing it.
science.
Isn't it on Green Lantern? Something about a black hole.
What?
What's
That's
this
a
movie?
Did you
movie.
send a camera in?
Called?
It would be crushed well before it got very close. I mean, the gravity is
Plus,
just
it would
so
take like 10,000 years
huge.
to get there.
It
Yeah,
still wouldn't be
yeah,
able
so
to-
it's too
it
far.
still
away.
wouldn't be able to see it either, right?
10,000
No,
Yeah,
years.
if you're
because
right
the
there.
absence of light would be a problem. Like
Put on a flash. I was kidding, this is the back.
if only we could solve it that easily. Wouldn't that be funny if somebody was just like,
Oh,
"Come
wait,
on,
what did
we'll
she
put a
say
flash
again?
on it."
Say it
It'd be
again.
cool though, like
I was
sensitive.
joking.
All right,
Small
get it together.
layers.
Put on a flash.
What is this
Ah.
comic camera? Wait, this is like ancient. And it's like state of the art right now.
And it's taking pictures that we could only dream of. Oh, I wish.
I wish
But
I
no,
could
we
time
don't know what the origin of the
No,
universe
bad
is.
idea.
Science cannot in any possible way come close to telling us how that happened at this point.
How would happen?
How, I mean, assuming that the Big Bang is true,
Oh, no, it's not.
Woo.
Obviously, we
don't
know how everything happened.
we have no
God
idea how
created
that
it.
was.
God made it with
Right.
his words.
Right.
He was just like,
Spoke
hey,
it.
But scientifically, we can't show
move, okay.
what started it at this point. So that's what it is. But anyhow,
Yo.
first law of thermodynamics, energy cannot be created or
Not that we'd be
destroyed.
alive,
So
but
if
could
this
we?
thing has potential energy, right?
Right.
And then I drop it, and all of the
Kinetic.
potential energy changes to kinetic energy until it gets to the end of its potential
And
energy,
then
right?
potential again.
Well,
What?
relative to what?
Ground.
Once it's
An earthquake could happen and then shake the ground.
Right, if the ground did split, it would then again have
Or-
potential energy.
yeah, but it has
Someone
but it has
tripped over
potential
it or
energy
something.
because you
Kicked it up in the
give
air.
it potential
Like
energy
it's so cool.
when you stop it.
Well, does it have the
Wonder if
potential to do any work right now?
No.
So can it have
Relative
zero potential energy and zero kinetic?
And that's what we see with the first law of thermodynamics. Total energy is equal to kinetic energy plus potential energy. Now, we have to remember, what is this potential energy relative to? Now, we're saying it's relative to the ground, because obviously, once it gets to the ground, it doesn't seem to have the potential to do more work unless something changes. So, it has all potential and no kinetic energy here, and it has all kinetic energy right before it stops and no potential energy.
So everything that has mass is potential energy.
Well, this has mass, but it doesn't actually have any potential energy relative to anything right now.
But,
It used
so
to.
would you say that
Yes, it
once
does.
it's on the ground, like relative to the ground, there's zero potential energy?
Zero
But
potential
like if someone
energy.
came along, kicked it, then
Or
whatever.
Right, I mean, if its circumstances changed. But once it uses its potential energy, it's converted it all to kinetic energy. So then we see that the first law of thermodynamics is true based on
So wait,
this
if
conversion.
if it's sitting on the ground, if it doesn't have any potential energy because it's on the ground, then does it have kinetic energy? But it's not moving.
But it did move, it converted all of its potential energy to kinetic energy.
But then it used
But
all
then it
that
was
energy
stopped
up.
by the ground.
So does it have no energy now?
Relative to the ground, right?
Relative to the ground, it
Has
doesn't.
zero.
But of course it has energy because its little molecules are moving and vibrating and, but we're not considering that right now.
But like total mechanical energy, does it have zero?
How about we stop asking questions?
Yes.
Okay.
Okay,
There's not gonna be a question like that.
that could be a real trick question right there. If
Double
there is,
check.
I'll give you warning next class, cause it's our first day of module 8. I will look at the test book. Right. So, if I'm sitting here at the top of this cliff, what's my potential energy?
Everything is zero.
All it's got. And
Mass.
what's its kinetic energy?
100%. Right.
1/2 mass times velocity.
Well, but it's not moving.
That's good. Wait.
Potential energy?
Kinetic, sorry. Well, kinetic would be 1/2 mass times velocity.
That's what you
squared.
asked
Should
for
be
is
zero.
kinetic.
Right, so it's 0 right now because it's got no motion.
But once it starts to
Because of velocity, what?
No.
showing everybody?
When during Christmas
You
break, I'm
can.
gonna be able to come back to the first class
You just-
afterwards. Then I'm gonna be gone the next Tuesday because
Okay.
my family
You
will
wouldn't
go
even-
on campus
you
because
wouldn't
Tom's coming over to Texas.
Oh,
Skiing.
fun. Very
I don't know
fun.
if there's anything I need to do.
I'll send you the video, since we
Okay.
will have a
Yeah,
video
he would hit
anyway.
that ramp and not even
Um,
come close to coming down.
So, here, Andrew,
Oh,
zoom in
sorry,
on
we
this. So, this has, all of its energy is potential energy relative to the floor. It doesn't have any kinetic energy because it's not moving right now. So then if it starts to fall off the table, okay, and then it begins to move, it gets halfway. So half of its potential energy at the halfway distance point, displacement point, has converted to kinetic energy. Half the potential energy is converted to kinetic energy. And then the other half of the potential energy is used, and it has zero potential energy, and everything that it had as potential energy here is converted to kinetic energy the second millisecond before it
But what
lands.
happens to that energy? It just
Mechanical
is used
energy?
up, and I'm so confused.
Well, it does work. It
Exactly.
moved a mass through a displacement. It moved a mass through a displacement.
Do the face.
Also, it displaced air molecules and all sorts of things like that that we're not talking about because that's air resistance, and we ignore that. Anyhow, what is its velocity? So this goes back to like module 4. Right here, what is its velocity?
Zero.
Okay, velocity is 0. What's its acceleration?
9.8 meters per second down. Squared. Down.
Right. And then at the halfway point, what's its acceleration?
Same.
Half of each.
Oh, thanks. What's its acceleration right here?
0.
9.8.
9.8 meters per second. Go straight down. Just acceleration in the y direction is constant due to gravity. So
Always.
don't forget that.
So
in the
always
y
9.8.
direction. Always.
Always
Something's falling.
9.8. Yeah, that's him.
32 feet.
Remember, we learned that when something's falling close to Earth, that it experiences a constant acceleration. So that's one thing you know in all of this. And what happens to velocity as it goes from here to here?
It gets bigger.
Continuously increases. And what happens to its acceleration?
It stays the same.
It's constant, 9.8 meters. Again, I repeat myself, but sorry. Okay. So, if we look at just objects falling, having kinetic and potential energy, that's one thing. But there are other systems, like springs and pendulum, that also have potential and kinetic energy. Systems that oscillate. So we're going to talk about pendulums today, and I think springs in a later module. I don't think springs are in this
Pendulums
module.
are like
Pendulum.
Mrs. Matthias,
something like that.
before I forget, this is for you.
Oh, thank you.
You're welcome.
Merry Christmas.
Thank you.
For you. Don't steal my
Well-
Merry Christmas.
I had a very
Season's
fun time
greetings.
in Smith
I'm
House,
sorry.
too. Season's greetings. You can say Merry Christmas to me, goodness. So,
Happy
we
holidays.
have a pendulum here. So we need to talk about some vocabulary about pendulum. So when you displace a pendulum, for it to oscillate in a predictable way like we want to look at, you can't displace it a large amount. I want to say less than 30 degrees. I think your book tells you. You can't displace your pendulum more than a certain
Wait, we
small
haven't
amount.
gotten to pendulums yet.
Well, when you get there, we'll find out what that
Okay.
exact angle is. But less than 20 or 30 degrees. So we're not going to look at a pendulum system that's out here like this. It moves differently.
Why?
So beyond
We're
this,
doing an
this square
experiment
six,
today.
6, 2. So here we have a pendulum. We displace it a little bit. The distance from its equilibrium point to the displacement is the amplitude. Just
How do
like
you measure that? I mean, that's kind of very imprecise.
yes, and we're only kind of looking at this and this little lab activity that you're going to write a little lab report about. We're only looking at this, not in numerical terms, qualitatively only. But you displace your pendulum from the equilibrium point to the amplitude, right? And it swings. And it has a predictable period, as long as I'm not doing this, which I kind of am, because it's so tempting. and it has a predictable frequency, right? Period and frequency are inversely related. It won't have quite so predictable a period until it gets to that low
Oh,
angle.
it's because like when you pull it up that far, it falls straight down before the
Right.
string catches it, so it's like
Oh, kind of like
Yeah.
a rope swing or something.
Yeah, it has a,
Oh,
it
like
has
when
a
you start swinging too
Y
high,
component
and you
to
like
its velocity.
Yeah.
No,
sort of
yeah.
hang in
Tight.
midair, and then you like jolt yourself.
Yes.
What if you pull it tight though? So it just,
Usually
It
when
still
that
is
happens,
gonna
I
have
just
that
jump
Y
off.
component. Did you
Okay.
see the drop?
Yeah.
Or like on a
And
swing.
it's not just because I'm clumsy about doing it, it really, it's
really does
very
it.
difficult to measure. So, anyhow, this is a system where you convert and reconvert from potential to kinetic energy. So when I'm at the amplitude of motion for this pendulum, what do I have in terms of kinetic or potential energy?
both.
Is it moving?
No.
Potential.
Just potential energy. So at the amplitude, I am at full potential energy on either side, right? Because there is a point where it actually stops and changes direction, stops and changes direction. So all potential, no kinetic energy. So how about at the amplitude?
Isn't it midway, like half potential and half kinetic?
Well, do I have, if here's the amplitude, do I still have any potential energy before I get to the equilibrium point?
Yeah.
Yes, I still have some potential, some kinetic.
Why do they use big words like equilibrium?
I know, but that's
The
the way
equal
it is.
place or something like that.
The middle point.
The middle.
The equilibrium point, because scientists love big words.
Would it be
I don't like
straight
scientists.
down? It wouldn't be quite
Sorry.
straight down, right? Because it doesn't go as far up the other side.
Well, we're ignoring air resistance.
But I mean, like even from the
I
gravity,
touched Josh.
right? Because it goes down and then it goes back up, but it doesn't go quite as far up as it was that side.
If we ignored air resistance.
So it would, if there wasn't any air resistance, it would go as far up the other side. Oh, okay, that's cool.
What
Yeah, 'cause
about,
gravity's
So go on
providing its
forever?
acceleration, it's keeping it going.
so if there was no air friction, it would just keep going, gravity wouldn't slow it down at all?
like if you stuck in one like a
Ooh.
vacuum or something like that.
In a vacuum, assuming that we could get
Well,
a complete vacuum.
there's still gonna be some air resistance, but like eventually it would last a lot longer.
Yes, but if we really did have a complete vacuum, it should keep going because gravity's what's accelerating it.
Oh, that's cool.
And air resistance is what's stopping it for us. But if we ignore air resistance, then the amplitude would stay the same, and it would have all potential energy here, all kinetic energy here, all potential energy here, all kinetic energy here. And then halfway between, it would have converted some of its kinetic energy to potential, but it would have some kinetic and some potential as it goes between, right? So, what kind of motion would you see here? Is this translational, rotational,
Rotational.
rotational motion?
So it wouldn't be like complete.
It's not equilibrium, right?
It's not in equilibrium because of air resistance. Would it be in equilibrium? This is simple harmonic motion. Would it be in equilibrium? I had to think about
What
that.
if you had the
Gosh,
no air resistance? It would keep on going to the same points, but wouldn't make the whole rotation.
Right. So for rotational motion, what's the definition of dynamic rotational equilibrium? The net sum of the torque. Oh, I know, this is such a geeky conversation. The net sum of the torque on the system is equal to
Net sum
zero,
of the
right?
torque.
Yeah.
So is the net sum of the torque equal to zero if we had no air resistance?
Possibly.
What if like what if a scientist talked like that, like all throughout their life? In normal conversations, like the sum of the torque of the air resistance with
Don't we all talk
On
like
my
that?
children as they walk to the school bus.
The state
No.
Is
in
this
which
why my
the sum of
children
the
look
Andrea,
torque
torque is
acting
with-
on
I know.
is zero.
You stink at sounding
I
smart.
If we
have
have
to
the
think
net
of
sum of
something
all
every
torques on
day.
this,
Ish.
If it's
I guess
constant,
if there's no
yeah.
air resistance, I think we do. So
Okay.
I think this
That's
is
kinda
torque.
rotational
Wait,
equilibrium.
torque is like
Torque is force times the,
Lever on.
yeah. the
wait. So what do they
distance.
mean when they say like
Does that mean we measure torque in joules? Because it's Newton meters?
torque?
Newton, I don't think.
Isn't there like another word for torque? Like something that has to do with like
Or was
bars
it
or
Newton
something?
kilogram?
Wasn't
What?
it? It was
Torque?
Newton meters,
Torque?
wasn't it?
Isn't that like something?
Oh yeah. I was wondering. So like
Close?
with all those Newton meters that we were writing, are those actually just joules?
Yeah. I don't know.
Turn off the camera so I don't have to answer that question. on
Here,
camera.
it's like it's not even here.
Wait a minute.
It's just on
Oh my.
Wait, what was the question?
Yeah.
A Newton meter is a joule, people.
Okay.
That's weird. So we could, instead of writing it all out,
Sure
a
you
Newton
can.
meter.
I just wrote NM.
Yeah.
I just
Yeah.
It's still shorter.
I do n times m because you don't want to get confused with nanometers, even though that would be a lowercase n times
Sweet.
n. I don't know.
A Newton joule.
I'm all stuck now. So yeah, I think this is
Joule.
a Newton
possibly.
times a Newton
Newton
times
joule.
a meters and Newton joule.
You sleeping?
All right. So anyhow, make sure you know. Sorry, amplitude, equilibrium point, all potential, all kinetic. So if there's no potential energy when it gets to the equilibrium point, why does it keep moving?
Momentum.
Cause,
Ah, yes.
okay.
Because it already has a velocity, which just keeps going.
It's too simple.
So, there is a list of questions for this lab experience that you get to write a discussion
Oh, this was a lab?
about. Yes.
Yeah, we've been doing a lab this whole
Yes.
time.
It was like a sneaky lab. You have to write a discussion about this lab, but just a discussion, nothing else.
Okay.
We'll have 8.1.
8.1. Okay, so, and use words like amplitude and equilibrium point for fun.
And torque and
No torque. You probably don't have to talk
Discombobulated.
about torque at all. So, just to review, Josh, what's the potential energy here? Maximum or
Don't-
nothing?
I don't know, Sam. Sorry. Zero.
Potential energy? Does it have the potential to do work?
Yes.
Okay, so its potential energy is maximum. And then how about here before it gets to the
Minimum.
equilibrium point?
Minimum
It has some,
half.
I don't think we can quantify, but it has some potential and some kinetic energy, because I don't know if I'm
But are
going
you
to
talking
have-
about like you're actually holding it as just so you know,
No,
or just a point?
No, this is a point in the
Oh,
rotation.
then it just has some.
It has, right, all potential, no kinetic, some of each. And
Zero.
then zero what? Potential.
Potential energy.
Zero potential, and how much kinetic energy does it have?
9.8.
Nope.
That's
That's
gravity.
acceleration.
Or acceleration. What's gravity?
9.8 meters per second squared straight down. But that's the acceleration. And
Okay, acceleration.
But you're not worried about acceleration. You're worried about how much kinetic energy does it have. So if you think about the first law of thermodynamics, that energy cannot be created or destroyed. However much potential energy it had at the amplitude, that's how much kinetic energy it has at the equilibrium point. Because no energy can be created or destroyed.
Oh, okay.
Right?
So it's the same as
all
up there.
still
as it is
It's
up-
all potential here and all kinetic here, but it's exactly equal, ignoring air resistance.
Okay.
So we know air resistance is real, and it's going to steal energy from our system, right?
Right.
So where does the energy go? Because it can't be created or destroyed.
Into your arm.
No energy. Hopefully.
Into the
I
air.
don't know.
Well, how does it go into the air? How does energy get lost into air resistance?
Because
The air molecules absorb it? I
Yes.
don't know.
Friction? Which
this
is
is weird.
It's
friction
kind of
in
like
air
friction.
cause-
Air resistance. So this is banging into little air molecules, right?
Really?
Yeah.
So my arm is banging in the air molecule.
Yes, if
Whoa.
you're doing work on lots of air molecules. We're all doing this now, Sam. And
This
so
is cool because I
you
can
are
feel
doing
it,
work.
it hitting the air molecule.
yes, you're doing work on the air molecules. The air molecules are increasing in energy because you are giving them energy. And then, so the energy that is leaving this system is going into the air molecules by causing them to move faster.
So that's why on the swing, if you don't do anything when you're really high up, you just slow down.
I didn't follow that.
No, when you're on a swing
Oh.
and you're swinging and you're up at the top and you think that you'll stay at the top if you stop kicking or whatever, and then when you stop kicking, you just.
That's gravity.
Oh.
I mean, that's like a pendulum.
I thought that was like air resistance.
Well, air resistance
That's
slows
what
you
makes
down.
you
That's
stop.
why you have to keep pumping on a swing. Air resistance slows you down. You have to keep pumping to
Told you.
add energy to the system.
Yeah, you did. You were asking me the question and you were scared to ask, so I.
What is this question?
Okay. So I still don't kind of understand how gravity causes the motion, because like I see how it comes down, but then how does gravity make it go back up on the other side?
It doesn't. All the potential energies convert to kinetic energy
okay.
here, but it has momentum. It's going to keep
I
going.
understand now.
It wouldn't just stop at the bottom. That'd
Right,
be
it
weird.
can.
Okay, I'm
I
sorry.
mean, it might not be weird, but we're used to it
Right.
keeping
So-
going.
We've got potential energy converted to kinetic, converted to potential, converted
Okay.
to, yeah. to
But
kinetic.
if it was like on the edge of a black hole or something, and if it came down, it would just stop. Because it
Oh, please.
I think you just
Dude, I'm getting so confused. I got like a headache.
Okay,
Black
so.
hole.
gets sucked into
Oh, so
a little
what-
pendulum.
Here's what Lab 8.1 actually says to do. It says to suspend this from something like the ceiling, which has not gone well in past years. You can ask your brother.
They hit him in his face.
No, it hit me in the face.
Oh gosh.
Aw.
And so I never let other people do this, of course.
Oh,
So
so
you're supposed to touch your nose with it and then let it swing, and it never comes back all the way to hit you due to air resistance. That's what Lab 8.1
are you
says
sure
to
it
do.
could?
Well, if there were no air resistance, it would return exactly to the amplitude at which I dropped it.
I wish there wasn't any air resistance.
But also, why does
But
it?
hit me
No,
why?
no.
Why
I
does
mean
it
like
swing kind of crooked?
that would be awesome.
because I can't.
Because
No, because then
You could breathe. You.
no, if there was no air resistance, you know how awesome that would be if we could like go on a swing and swing from the top,
Forever?
like on
How
a
would you
rope swing,
stop?
and we could just swing forever.
Well, you could stop with your muscles. I mean,
Oh, yeah.
Well, I mean, then
Jump
like
off.
every like fighter pilot that has to jump out of his plane would die because unless he had like a
you
rocket
wouldn't
pack
get the
as a
plane up
parachute.
Oh,
without air
yeah.
resistance because to go the air.
Oh yeah,
Might
so
have
there.
to
See, you
fly
wouldn't be
with
able to
air.
use planes.
We wouldn't be living if there was any air resistance.
There'd be no air if there weren't any air resistance. So that would be the bigger problem than not being
This
able
is-
to
Oh,
have
yeah, that's
lift.
true.
Right. So yay for air.
Says Josh.
Air.
looking dumb.
See, it makes you air resistant.
Okay, so why
How are
does the
you guys
pendulum
doing?
never try to
I
return to
wasn't.
its original amplitude?
I was.
Oh, you just
Air resistance.
Air resistance.
Yes,
Air
you better not
resistance.
put this on
And
YouTube.
when you write, I know, seriously, I'm mailing him with this. When you write
He's
the
gonna
lab
think we're
report,
all
make
weird.
sure you relate both the transformation from potential to potential to kinetic, and the loss of some of that energy to air resistance to the law of conservation of energy, to the first law of thermodynamics.
Ooh.
So
Yes.
this is just a discussion,
Just a discussion
and
only.
there's no experimental error, right? Because we didn't really do an experiment.
No, because if we're ignoring air resistance, then there's no real source of error. And since we have air resistance, we just need to say the air molecules get banged into and gain the energy that is lost by the system.
Okay.
So then your lab report, all of this is in those that lab help sheet. It has the questions. What is the velocity at the amplitude? So when it gets to the maximum ends there, what's the velocity?
0.
0. It stops and turns around, stops and turns around, stops and turns around, right? So it's got a velocity of 0, increases, increases, decreases, decreases, 0. Increases, increases, decreases, decreases, 0. So velocity oscillates like that. How about acceleration?
Isn't it always 9.8 meters per second?
Well, but there's a tension too.
Do it 4
Oh.
times.
Here's where I've been
Yeah,
ignoring
break
your
out the
questions on
tension.
acceleration.
Break out the.
Nick, that's gonna
Would that be
put off
centrifugal
inside your
force?
skin and you'll be like
Yes,
that.
because
No,
this is
look,
rotational
your
motion.
neck is
So you
red.
have a component of gravity accelerating you all the time, but not full gravity because the tension on the string provides another force. And at every point, of course, that's going to be different, right?
Ooh.
I mean, gravity is only fully in charge at the equilibrium point. At this point, gravity is pulling one way, but the
Just
tension
zoom
in the
in.
string is pulling another way.
Good
So
to
is
zoom
that a
in.
sign of gravity or something?
Well, gravity is in the y direction, so use sine.
Do we have to do
X is
problems
always
about
friends with cosine.
pendulums?
What?
Do we have to do problems about pendulums?
Yes.
That guy in our book
Yes.
is weird looking.
I did not look at the book. So,
He's like,
last question. If there were no potential, I asked this question already. If there's no potential
Yes.
energy, it's all kinetic here, it keeps moving because of momentum. Because it still has a total energy.
crabs.
Alright, so let's look at some practice problems. And, review questions.
July 8.1.
The top of my review question sheet says this.
I'm so sorry.
Yes.
Okay, can I ask one more question? Okay,
No.
so when it says, the acceleration at the equilibrium point would be 9.8, but nowhere else it would be 9.8. You would have to calculate what it was at the other
Wait, are we doing
places.
review questions
Yes.
or practice?
Okay.
Practice?
Okay.
Review questions first.
Can I do number one?
Yes, but the top of my page says this. If you don't master these problems, it will come back in module 14 and be awful. So,
Master.
must master these problems.
Master.
Because module 14 adds a
Obi-Wan.
whole new fun layer of math to this math,
Master
so you
Yoda.
have to know what you're doing here. But then module 15 and 16 are super easy, so, you know.
So
Like-
we're just gonna be taking this test. Wait, isn't one like only 2 weeks or something like that?
So
Module
Or
16 we do in
will
1
we do
week.
them in like 1 week so that we have a whole week to just
We'll
study?
do 15 in 2 weeks because we do fun labs.
What about, but 16 we'll do in 1 week so we have an extra week
Yes.
to study?
Yes, I make
like-
chemistry do module 1 in 1 week, which is horrible, but
I remember
16
that.
is
I
awful
remember
too. So it's better to do it at the beginning than the end. But you guys have
Wait, is
super
there math?
easy at
I
the
can't
end.
believe we have to take a midterm in class.
You don't have to take a midterm in class.
Electric
Final.
circuit.
Final.
Do we even have a
Which is
midterm?
even worse
No,
than
no
midterm.
Wait,
midterm.
does our class have midterm?
Not this week.
When is it?
When we
have
come
to
back.
do the midterm.
No.
Like
No,
government.
we're gonna
Just
do
fail
it.
all
You-
the
I
bread
would-
tests
fail
and
it
then the
too.
final thing.
Unless I study.
Yes,
Yeah.
and
I
I
need to
would
write down
use
all
those
the,
quarterly
like,
tests as a review for the
I don't-
final.
For literature, I don't remember the midterm.
Use the quarterly
Probably
test
because
as a
you
review
got
for the
100 on it
final.
because you're smarter than us.
Okay, so
Do you know anything that like repels
The
carbon?
final was hard.
Repels
No.
carbon?
Because
why?
like Peter Weiser was trying to figure out how those like those hovered cars in Star Wars would work. And
They
he's thinking
would
if you
not
could find
work.
something
Oh.
that repels carbon, because carbon's in pretty much anything, so they could like hover and I don't
Just
know.
What, is he gonna
put
try
the
and make a
magnet in the
hoverboard or
bottom
something?
of it, and then you don't have to worry about the carbon.
Well then, not everything's magnetic.
Well, everything on your set can be magnetic if you're trying to do something.
Well, no, like an actual car to
If you
drive
mean
around.
metal roads.
Oh, magnetic roads.
I think
It'd be like
that we will have
Since
like
I'm not
hover
that
skateboards
Well,
and
isn't that how,
stuff
like,
like that
trains
like
are
later
going?
on in the year.
Oh yeah,
Yes,
there are
they
like
do.
those
They have
magnet.
magnet.
Yeah, so you can just make roads like that.
Hover.
We're talking about
And we will talk about that in
Star
module
Wars.
16, but
Hover
right now,
skateboards.
the girls are like,
Coming near
sorry,
you.
Sam. Okay, number 1 says.
What are you talking about?
Here
I
we
love
go.
Star
Josh, a
Wars.
secret agent is locked in a room. He pushes against the door but cannot open it. He falls to the floor exhausted. Has he
Stupid.
done work on the door?
No, he
No.
did not do work because displacement was
0.
zero.
How about distance?
The distance from the door to the floor?
No.
Oh.
The distance that he moved the door through, was it different than displacement? 0,
No.
both cases. No distance,
Zero,
no
bro.
displacement. Just seeing. Alright. Josh Morrison, 2 men attempt to move a desk through the same displacement using the same magnitude of force. The first has a rope to the desk and pulls at some sort of angle. The second pushes at a absolutely parallel to the floor angle. Which man will do the most work using the same force?
I would say the second guy, because he's obviously applying a lot more force.
You mean the man on the
like,
right?
Look at
the
his
guy-
face.
He's just like on the left, is like, and the guy
Okay.
on the right is like,
So just a note here, the problem says that they use the same magnitude of force.
I think I must be like.
Obviously,
well, this guy
the
must be like a
second guy.
weakling or something.
He's
Yeah.
really
Okay.
small.
Because he's a little
He's
girl.
really small. Like.
But
Look at his.
if they're using the same magnitude
Obviously,
of
because
force,
it's
what's
parallel
the
to the floor.
I know, look
Okay.
at this. Look at this.
difference? So there we go.
guy.
The second guy who's exerting more facial
That guy
effort
is
there
clearly has some muscle.
is doing more
Zach.
work because his force is
That guy.
all directed parallel, whereas that guy only a little bit of his force is directed parallel because some of it's directed perpendicular to the desk. Because you have to break it
Maybe
into
he was
two
trying to lift
components.
the desk.
Okay.
Turtles don't wear
Any
pants.
questions about that?
No.
Oh, what kind
They
of
don't.
equilibrium is the motion of the desk?
Turtles
Any
don't wear
kind?
pants.
Did he?
This guy.
Either guy, because they're using the same magnitude of force. So, even if the angle makes the force on the desk parallel to the floor less, it's still a constant force. What kind of equilibrium is the desk in while it's moving?
Dynamic.
Translation.
Moving. Translational.
Dynamic,
Well, are they
translational,
even
2
pushing
words.
it, or are they just
They
like?
said
Pushing or
they're
pulling doesn't matter.
attempting
Attempting.
to.
Because that one guy looks like he's straight and
Oh.
he's not doing anything. So
Well,
it could be
that's-
static.
It's because he's fat and out of
So,
shape.
okay, if the desk isn't moving, what kind of
Static
equilibrium?
translational.
And if the desk is moving, what kind of equilibrium?
Dynamic translational.
And how do you know it's in equilibrium?
It's not the sum of all torques equals 0.
Well, that's rotational, so we're not worried about
Pushing
the
it in a
torque.
circle.
So we're worried about what? To see if we're in
Sinus
translational
right
equilibrium.
What?
How do we know if we're in translational equilibrium?
When it's moving at constant velocity.
Constant velocity. Is this desk moving at a constant velocity?
Yeah.
Yeah.
Why, how do you know?
It's not
Because it's
moving.
not moving.
It's not moving.
It hasn't moved in a while.
I mean the desk in the picture. If it is moving.
I thought you were
He's
talking
taking a
about the table.
painkiller.
Wait, you're taking a painkiller, really?
Yeah,
He cut
for my
his
thumb.
thumb off.
Cut
cut your thumb-
No, I didn't cut it off.
Sam, he cut his thumb off and
No, I did. It's right here.
I ate it.
So anyhow, so if a constant force is applied to the desk, is acceleration constant?
No.
If it's not moving.
If it is moving.
No, yes.
It could
his
be.
Acceleration is 0.
Thank you.
Okay, so if he's applying a constant force to the desk, if force is constant, if F equals ma, and mass is constant, well, force is constant, mass is constant, what do you know about acceleration?
It's also
It's constant, right? 2 can't be constant without the other one being constant. So, acceleration is constant, that means velocity is what?
Changing.
0.
If acceleration is constant, velocity is changing.
What?
You
Yeah.
just said that. Is it true?
No.
No, it is.
Wait.
I'm
If
so
acceleration is
confused.
0.
No, constant.
Oh,
Not
constant.
necessarily.
Oh yeah.
They're
it's
constantly
changing.
accelerating, getting faster, so
That's
the
right.
velocity can't
So-
be the same.
I
So
thought we
if
said it
you-
was constant at
If the
0.
desk is moving, is it in equilibrium?
But what if the acceleration is downwards? Like
You've already
Well,
acceleration.
we know that the desk
57
is
minutes.
moving.
Oh, we're still talking about
We're
this.
talking
one.
about the desk.
No, but
Okay.
like I thought you said that the acceleration was 0. It should be constant because it's not. The acceleration
No, that's
is.
what somebody said. I just
Oh.
repeated that.
Oh, okay.
But you're getting here. You're bringing it home.
Good
So,
job, bring
If
it.
acceleration is
Come on.
constant,
You're rounding third base. Bring it home.
if acceleration is
second
constant,
base.
what's happening to
Or
velocity?
first.
It's changing.
Or between
So
first
is it
and
in
second.
equilibrium?
We're on problem 2.
Um,
That's second
no.
base.
No. So
There's
if the desk
6
isn't moving,
bases.
you're in static
Translation.
translational equilibrium. If the desk
In
is
baseball.
moving, acceleration is
Only
constant,
4.
velocity is changing. The desk is not in equilibrium. Sorry, just have to review that.
Yeah.
Think, you know.
5 bases.
Number 3, what are legitimate units for energy?
Inch pounds.
Nick.
Inch pound. Oh,
Inch, pound, and Newton kilometer.
nope.
Yes.
Got it wrong.
Good job.
He's
wrong.
right. Inch pounds, because what is energy?
Wrong.
What times what?
Weight times distance.
Weight times distance. Weight times distance. So,
Or distance times.
distance times
Yeah,
weight.
both of those.
So, in this
For the
case,
drinking one.
Newton is a weight. Ah,
We only have 5
that's not
minutes.
good.
Practice
We haven't
problems.
done
We'll
any
do 4 of
Class
them.
is shorter today.
Oh.
Oh, because the dumb Christmas.
That's not good at all. Okay, I won't harp on that one anymore. Let's do at least one problem.
Can we do the
Number 4.
Number
or 4?
4.
Oh.
Absolutely.
Yep.
wait?
That's
Number 4 was easy.
lovely.
I'm not
Christmas
confused.
party.
Okay.
Number 4 was easy.
It's
So
lovely.
in number
I only
4,
got the
we have a
first
car
part.
going down a hill. This is very similar to the lab we'll do next week too, and that should
We
clear a
didn't
lot
do
of
5
stuff
and
up
6.
for you.
Dilated.
We only had to do 4.
Um,
Hey, does that pain medication make you feel weird?
No,
A little woozy.
What if I punched you in the face? Would you feel it?
I imagine I would.
Oh. So it's not
Let's
like
don't though.
it's not like strong medicine.
It's
No,
for his
but
hand.
apparently it's just making me not able to concentrate.
What is it called?
No, Josh, goodness gracious, a car
Don't give him
travels down, don't feed him any information. A car travels down a hilly road, boys. At the top of an 11.5-meter hill.
Stop. You didn't understand the problem. You need to focus.
I got the
It's
first
11.5
part.
meters.
Showing them the
I'll do the
picture.
camera.
Okay.
Alright, 11.5-meter hill. With me?
Yes.
It's traveling with a speed of 21.4 meters per second. So here's our car. 21.4 meters per second is our velocity. Okay, so it says the driver decides to let the car coast down the hill and up the next hill. If this hill is 5.1 meters high, then how fast will the car be traveling at the top of that hill? Okay, so we need to calculate what? What do we know about this hill? Does this car have kinetic energy?
No.
Well,
Yeah, height.
it's moving, right?
Oh.
I
Which one are we
thought
doing?
It like stopped.
Number 4.
Okay, there was another problem where it stopped
Wait,
at
number
the top
4?
of the hill. Never mind.
Okay,
It does have kinetic energy.
so this car is moving. It has kinetic energy. Does it have potential energy?
Yeah.
It's moving. Or
Even if
Some-
it
some,
weren't.
Yes, it does.
Even if it weren't moving, it's at the top of a hill. That gives it potential energy relative to everything below it, right? Okay, so it has both. So let's figure out what its potential and kinetic energy is. The kinetic energy is 1/2 mv squared. Potential energy is mgh, right? Okay, so do we know the
Number
mass?
4.
For
Yeah, no, we don't. That's what we don't know.
Okay, so we just know that this is 1/2 times m times velocity squared, 21.4 meters per second. Then we know this is mass times gravity times height, which is 11.5 meters relative to the ground, right? So, then we can say the total energy of this system, according to the first law of thermodynamics, that energy cannot be created or destroyed, right? Total energy of any system has to equal its kinetic energy plus its potential energy, right?
Mm-hmm.
Alright, so let's see what we're doing. Alright, so we're going to say total energy is equal to both of those things added up. 1/2 m times the velocity, 21.4 plus m times g.
Don't forget to square the velocity.
Oh yeah, you fixed it.
Oh, this guy. Alright. So, we've got that, right? Now what do we know about this hill? Do we know anything about that hill?
The same thing.
Same thing.
So we just do that again?
Is the total energy going to be the same here as here?
Yeah.
Yes. Okay, so at the top of this little hill, total energy can't change because energy can't be created or destroyed. It can only change form, right? So, total energy at the top of this hill has to be equal to the kinetic energy plus the potential energy. Well, I'll just write that. So total energy here is equal to kinetic energy, which is 1/2 m times velocity squared plus mgh. So we don't know mass, we do know gravity, and we do know the height, which is 5.1 meters, right? So we're going to set, let me change colors 16 times. We're going to set the total energy of the system at the beginning equal to the total energy of the system at the top of this hill because, of course, no energy is created or destroyed.
Well, then can't you just cross out both kinetic energies because they're just like they're the same on both sides?
Has the velocity changed? That's what we want to solve for.
Okay, so we don't want to
Is-
cross those off.
Right, this second velocity we want to solve for, v sub 2. So this guy right here is what we're solving for. Okay, so 1/2 m times the initial velocity squared, that quantity, plus mass times 9.8 meters per second squared times 11.5 meters is all going to be equal to the kinetic plus potential energy at the end. Now, what do you see in every single term of this equation?
You can cross out the meters. I mean the mass.
Yes, thank heavens. We
Because
get
having
rid of
two M's
mass.
in there is very confusing.
Yeah, I'm gonna, poor Sam, I'm going to, oh, that's a meter.
Like we said,
Yes.
very confusing.
All right, so I'm gonna rewrite that with all the M's crossed out in a new color. All right, and I'm gonna erase that thought. All right, so 1/2, thank you, times 21.4 meters per second, that quantity squared, plus 9.8 meters per second squared, times 11.5 meters equals 1/2 times velocity squared, which this guy is what we're solving for,